Bohr's model, as we said, was great for the hydrogen atom, but the problem is it's the only atom with one electron, and Bohr's model didn't do very much in terms of helpfully explaining the behavior of the rest of the elements in the universe. So, something called the wave mechanical model of the electron was developed by de Broglie and Schrödinger, and they focused on the wave properties of the electron. If you remember earlier, we said the electron, being a medium-sized particle, can exhibit both wave-like properties and matter-type properties, and so they focused on the wave-like properties of the electron to help explain why the electron stays where it does relative to the nucleus of the atom. They said the electron behaves as a standing wave, and only certain wavelengths fit within the circumference of the atom. So you've got a particular circumference of a circle. You can only make a certain number of standing waves fit there if the wavelength has to be a certain length. And so, depending on the type of standing wave generated, this could be used to help explain the allowed energy levels of the hydrogen, because only certain wavelengths can be allowed in the circumference, only certain energies could be allowed for the electron in its particular energy levels. So if we look at this diagram, we have a particular wavelength for our electron, and for n equals 1 we have one wavelength. When we have n equals 2, we have two wavelengths. So if we take them and straighten them out, we see the strips shown on the left. If we curve these strips then into a circle, we get circles of specific circumferences based on the number of full wavelengths. So if we take a top-down view of this now rather than a sideways view, what we get is something like this. So on the left we've got the red being wavelengths. So a wave would start here and follow around. So that is 3 wavelengths. The other half is a standing wave. It's the inverse of it. So we have both of them. So we have 3 wavelengths for this circumference. We could have 5 wavelengths for this circumference if the wavelength were shorter. 3.3 doesn't work because we don't have an overlap. We don't have perfect wave pattern matching. So that would be not allowed. That would not be an appropriate energy level or circumference for our energy level for the electron. Okay, Schrödinger developed math equations to describe the path of the electron, the probability of finding the electron in a particular path or location. They're not definite spots within the atom, they are probability regions. So for Schrödinger's equation for a single particle, that'd be an electron, moving in direction x, we have an equation very much simplified that looks like this. So those of you that are in calculus will see that we're taking derivatives here. So we have the second derivative of phi divided by the derivative of x squared, and then we're adding a bunch of constants here. E is the total energy of the electron. Psi is the wave function of the electron. In this particular equation, V is the potential energy of the electron. It's the energy based on the position of the electron in the atom. And then M in the equation is the mass of the electron. H is Planck's constant, and pi is a constant as well. Since the atom is three-dimensional, not just one-dimensional, Schrödinger's equation came up with similar equations, similar patterns for the y direction and for the z direction. So in order to describe in 3 dimensions the likely space to find an electron, you need to solve all 3 equations. Fortunately for us, we're not going to have to worry about that. Okay, the psi function we saw before is the wave function, and it describes the orbit of the electron. And the electron doesn't necessarily move in a circular orbit, it moves randomly. We don't know exactly how or exactly where it moves. And the Heisenberg uncertainty principle helps us to explain that a little bit more. Heisenberg was another one of the people that worked on the wave mechanical model, along with Schrödinger and de Broglie, and he determined that you can't know the position of the electron and its velocity. You can figure out one, and that causes the other to change, or you can figure out the other, but the first one changes. So you can't find them out both simultaneously. You can approximate it, but you can't find inequality. Okay, velocity is distance over time, so that's what our equation tells us. If I want to find the velocity of a particle, it has to move from point A to point B, then it's no longer in the same position. So I can't find out where it is if I want to know how fast it's going. And I can't find out how fast it's going if I know exactly where it is. So Heisenberg came up with an equation to approximate the momentum of the electron. Heisenberg's equation looks like this. We have the change in position. X represents position. M is mass. V equals velocity. Mass times change in velocity is momentum. So I take the position times the change in momentum. And notice it's a greater than or equal to, it's not just an equal to's equation. H again is Planck's constant, and then the pi. Okay, so this is the minimum uncertainty of a particle's position and its velocity. So we can try and approximate both of them at the same time, but it's an approximation. Sidney Harris felt the need to explain Heisenberg uncertainty principle in this cartoon, so he's talking about railroads. Okay, the wave function, it turns out, is not very helpful because you can have negative and positive values for a wave function. So what it turns out is psi squared gives us the probability of finding an electron at a given point in space. These are going to be all positive values because when you square something, that's all you end up with. So there are three ways of representing the likelihood of finding an electron at a particular point in space. The top diagram on the right is a probability plot for finding electrons, so just taking a bunch of points in space and identifying where we're likely to find the electron relative to the nucleus. Most of the points are within a 90% probability circle, so essentially what you do is put all the points in and then figure out where 90% of your points are located. That's how the circle's determined. If you were to graph these distances from the nucleus, you'd see the middle diagram. So on our vertical axis we have the radial probability of finding the electron relative to the nucleus. Along the horizontal axis we've got the distance from the nucleus. So at 0.053 nanometers, that's where we're most likely to find the electron in a hydrogen atom. That essentially defines the radius of the hydrogen atom because the electron cloud is what determines the volume of the atom, and where I find those electrons gives me the radius. So three-dimensionally at the bottom we see this semi-solid type sphere showing us a 90% probability region for finding the electron, so approximately the radius of that hydrogen atom. Radial probability distribution of electrons can be looked at for atoms with multiple electrons. So what we're going to look at in our graph is bumps, and the number of bumps tells us the number of shells. So if we compare a 1s, a 2s, and a 3s shell, what we'll see for radial probability is a single probability bump for 1s. For a 2s electron, most of the time it's going to be at this larger distance from the nucleus in the 2s orbital, but sometimes that electron can trade places with and therefore jump down and exist in the 1s orbital. So there's a bump there to indicate that this 2s electron that normally hangs out in the second energy shell can sometimes hop down and exist as an electron in the 1s, or the first energy shell. Same is true with the 3s electron. Normally it hangs out at the third energy level, but it too can sometimes migrate and trade places with electrons in the 1s or the 2s shells, so it has some small probability of existing and being found in lower energy levels. How do we know this? Well, if we can tag electrons, we can follow where they are in space relative to the nucleus. The maximum value of 5.29 times 10 to the negative 11 meters is the smallest Bohr radius for a hydrogen atom. And what we define an atomic radius to be is when the electron is at a distance with 90% probability. So again, the electron cloud defines the radius of our atom, and it's 90% of the likelihood of finding the electrons at that radius that define the radius of the atom for us.